Okay, so this time we're going to look at what we call goodness of fit. And we're going to look at the one sample. The two sample you'll see in the notes is when you want to compare two categorical variables and see if they're independent. But the one sample goodness fit is often we'll get some data. We'd like to ask the simple question of, is it consistent with some probability model? So rather than do a lot of derivations this time, we're actually going to have a go at doing a little bit of code to have a play with this and see how good it is. So we're going to start with the classic one. So suppose now that we observe a multinomial data y1 up to yk, and we basically believe that the probability of y1 is certain value, y2 is certain value. So our null hypothesis is that the probabilities of each of these levels is equal to some given one. And then what I can do is I can go, right, let's take each value minus off its expected value. So to get its expected value, you would basically take the probability that we think is in the null hypothesis, times it by how many, square it and divide by the expected value. Add them all up and get that. So this is basically measuring the squared distance between the observed data and the expected data. And we've normalized by the expected data. And if the null hypothesis is true, then this thing here, which we call the chi-squared, will have an approximate chi-squared of k minus 1 degrees of freedom. The k minus 1 is because the probabilities must add to 1. Once you've set k minus 1 of them, the final one is set. So you only have k minus 1 degrees of freedom. And then we can do a one-sided test to see if we should reject or not. So the classic example of this is, let's test if we have a six-sided die, whether it's fair or not. So imagine I've got a six-sided die and I've rolled it all together 48 times, and 8 times I got a 1, 10 times I got a 2, etc. And the question is it fair? Is each side equally likely? So first of all, we've got some data here. So let me go to my code over here. Let's read in the observations. So here's my observations, 8, 10, 9, 7, 7, 7. Now, if the die is fair, then each side, so the probability of getting a 1 is the same as the probability of getting a 2, or equal the probability of getting a 6, which is a 6. So what's our expected probabilities? Well, let's do that. I'm just going to use the rep function. So my pi 0 now would be a 6, a 6, a 6, a 6, a 6, a 6. So how many observations did we have? Well, we already said that that was n, which was 48. And so I can basically say, well, what's the expected number of, for example, 1s and 2s, etc., by just multiplying the probability by the total number. So basically, I expect, on average, 8 times I roll a 1, 8 times I roll a 2, 8 times I roll a 3, etc. So let's do the calculation. We take our first one. We observed an 8, so we go 8 minus 8, which is our expected squared, divided by 8. The next one, we've got 10 of them. 10 minus 8 squared divide. So here's my calculation to do that. So basically, I get a value of 1. So I've taken the observations, I've taken off the expected, I've squared them, I've divided by the expected, and I've added them all up, and I get a value of 1. So our x squared is 1. That doesn't seem very big at all. But how do we actually do it? We're going to do a chi-squared. So the degrees of freedom is 6 minus 1, so it's 5. We want to do greater than. You can see up here we've got a greater than. So we basically do lower tail equals false and do a p squared. And if I do that value, I get a p-value of 0.96. It's really large. Usually the standard is 5%, so it's less than 0.05. This is greater than that. So basically, we retain the null hypothesis. So I think this die is fair. Okay, not a lot of data there, so never mind. So let's ask one where we've got some bigger data. So we're looking at health and safety, and we've taken 414 machinists at a factory. So they're using a machine to make parts, and we've recorded how many accidents they have. So out of this, 296 of the employees have no accidents. 74 have 1, all the way to one unlucky individual who has had 8 accidents. And we want to know, could we represent this as a Poisson distribution? Is it a Poisson distribution or is something else happening there? Well, now we're going to have to change it because up here, I knew the probabilities. Here, we have to work out what Poisson would be best. So in that case, we're going to have to estimate a parameter. And the parameter we're going to have to estimate is the lambda of the Poisson distribution. So we need to adjust for that. So instead of being k minus 1, we have to take off every time I make an estimate parameter. So in this one, it's going to be k minus 2. So first of all, we're going to go and enter my data. So here's my little tibble. So I've entered the data. So we have the number of accidents and how many people did that. So what's the next thing we have to do? Well, I need to get estimate of the lambda. Now, you will know from earlier in the course you could use maximum likely estimator, and the estimation of lambda would be the mean. Now, I don't actually have the values. I'm just cheating here. I'm saying, well, actually, I need a vector that has basically 296 zeros and then 74 ones and then blah, blah, blah. So that's what this command here does, the rep. So if I run that command, you see, basically, it's made, so the first person had no accidents, the second person had no accidents, so all the way up to this person here had 2 accidents, etc. It's a quick way for me to cheat. So basically, I'm now going to take the mean of that, and that gives me my estimate of lambda. So our estimate is, on average, people have about 0.48 of an accident. Put that in. So what I'm going to do now is I'm going to have a look at the data. So here's the actual data. Let's just pop this up. Let's pop it across. Let's make it a bit bigger. So I've just plotted our data. So this is the moment this is how many people had 0 accidents, 1, 2, etc. No problem. Next we're going to get the expected value. So I'm going to take my Poisson distribution, calculate the probability of having 0 accidents, 1 accident, 2 accidents, etc. I just took the probability and I just rounded it to 4 degrees, to 4 places, and then I calculated the expected. So let's have a look at this data. So let's clean this up. So you can see generally do that again. So we observed that 296 had no accidents. The probability of a person having no accidents is 0.615, and so we expect that 255 of those should have had no accidents, etc. So next thing I'm going to do now is I'm just going to have a look at this data as a plot. So what we got here is you can see the brown line is what we observed, and the blue line is what we expect, and they match. But you can see I've got more 0 accidents than I expect, and the one is down. So this is interesting, and we want to ask the question is, maybe just by chance these are consistent, or maybe there is, because there's a definite possibility that people will not report an accident. So maybe they had an accident and didn't report it, so this has gone up a little bit and this has dropped down a little bit. I don't know, maybe you get in trouble if you report an accident. Hopefully not, but maybe you do. So we can test if that's consistent. So we've got our data, we've just calculated our expected. Now, this theorem only really works if you have an expected value of about 5 or more. You can see these ones are all very small, and you have a couple of problems there. So what we're going to do is we're going to truncate it. What we're going to do is to try and use that theorem to get the asymptotic chi-square behavior. All these ones that are 4.8, 0.6, 0, 0, we're going to collapse them together. We're going to truncate this. So this is what this is doing here. It's saying only grab the ones that have an expected value that is greater than 5. So now add up all the rest, and we'll pop them together. So what I've done is I've truncated. What we've got is all the ones that are 3 or more, I've truncated together. I've put all the probability together and truncated it. So now we can do the same calculation for our chi-squared. And now we get an x, which is 55. What's the degrees of freedom? Well, now we've got 4 levels. So it wasn't the original one, it's the ones that were actually put into the thing. We've got 4 levels. We take off 1. We had to estimate the lambda, so we take off another one. So it's 4 minus 1 minus 1. We calculate our p-value. and we get 8.56 times 10 to the minus 13. So this one basically says we reject the null hypothesis that this is from a Poisson distribution with that lambda of 0.48. It's close, but we need to adjust. In fact, what we'd probably do, and you'll see this in later courses, we will probably do a zero inflation Poisson model. Because in this case, I think we're getting slightly more zeros than we expect. Okay, that's all for now. See you next time.